rises. So why does our Earth spin in the first place? It's a question that takes us back to the very birth of our solar system, a story written in stardust and gravity. About 4.6 billion years ago, our cosmic neighborhood was a chaotic place, a vast, swirling cloud of gas and dust. Imagine an enormous ethereal nebula, pregnant with the potential for stars and planets. As this colossal cloud began to collapse under its own gravity, it didn't just fall inwards, it began to rotate. This is a fundamental principle in physics, the conservation of angular momentum. Think of an ice skater pulling their arms in to spin faster. The same principle applies, but on an unimaginably grander scale. As this primordial cloud contracted, it spun faster and faster, eventually flattening into a disk. At the center of this disk, the sun ignited, and further out, clumps of matter began to coalesce, forming the planets, including our very own Earth. The initial spin imparted to these nascent worlds during their formation has remarkably persisted. Once something is set in motion in the vacuum of space, it tends to stay in motion. There's virtually no air friction to slow it down, unlike objects here on Earth, so our planet has been spinning, a majestic cosmic ballet, ever since it was born from that ancient cloud. Picture a spinning top, a child's toy that whirls with mesmerizing stability. Now imagine that top never encountering the friction of the floor or the resistance of the air. It would, in theory, spin indefinitely. Our Earth is much like that super-powered spinning top. Unlike a spinning top in your hand, which eventually succumbs to friction and tumbles, the Earth doesn't experience significant friction in the near vacuum of space. There are some subtle forces, like the Moon's tidal pull, that are gradually slowing us down, as I mentioned earlier, but for the most part, Earth has kept rotating with incredible fidelity for billions of years, a testament to the powerful forces that shaped our solar system.